Okay, good morning, Astronomy 1020. It is our last week of lecture. Woo! The class is coming to an end. Stacy's a little excited. We have a lecture today, in a lab today, and we have a lecture and a homework on Thursday. And just to further the announcement that I made last week, I've decided that you guys have the option, should you choose to accept it, to avoid taking a final exam. And the way this works is, if you would like to not take a final exam next week, then I will take your midterm grade and use that for your final grade as well, which is probably close to what you're going to get based on past experience. So it'll just avoid the stress and the time consumption of it. Now, if someone wishes to take the final, I will of course oblige them because that's their right. But I need to know by Friday if you want to do it. Okay, so I think very few to no people are going to take me up on this option, but I want to make it available out of fairness. If you do take the final, that's your grade. Okay, you can't have it both ways. So either you skip the final and you'd use your midterm in place of that, or you take the final and you get what you get. Are there any questions about that? How many people think they'll be skipping the final exam? Yeah, okay. So that's what I figured. I figured most of you would rather. And I was talking to some of my former tutors last night. We had a catch up with the boys Zoom party or a Zoom meeting, I don't know. And I was talking to them about their school experiences, and they're all really stressed out, and they were struggling to complete their coursework from their bedrooms, as I'm sure you guys are. So I think it's fair. There is the same scale that we apply to the midterm. If you were present for that discussion, then you learned what my scaling system was. If not, you can go back and watch that video. But I'll average your homework scores, your lab scores, and then I'll average the midterm twice. And then once I get a percentage, like 65% or 70%, then I apply my scale. So as long as you've been doing your homeworks and your labs, you should be in good standing and everything should be fine. Another announcement that I really need to make, Friday is it, okay? That's the deadline. Well, I guess I could give you till Saturday if you really need it for the night students. But I am going to grade this weekend, and then I'm closing the books out, and I don't care anymore. Do you understand? Like at some point, the show has to end. And so I don't want to be getting an email like January 2nd with you trying to send me labs or something, because that'll just be ugly. Rather, I have obligations to turn in grades myself, right? So Blackboard tries to compute your grade, but it does it in a really awkward way. So in past classes, I've tried to go in and manually put your grade, but this year they increased each section to 28 people, which means I have hundreds of students. So I'm going to try to do that. Yeah, Reardon, but the problem is that they keep trying to like add columns and calculate weird. They try to average everything, but my labs are out of 25 points and my homeworks are at 10 points. They just do things in a very stupid way in Blackboard, and it's difficult to use that system. You guys can't understand how annoying, well, you probably do from submitting homeworks. Blackboard is an extremely irritating system to use. One last announcement before I start discussing stars. I have someone coming to visit me today that needs to be buzzed in about 15 minutes or so. So I'm going to keep this on ring, and I'll have to answer that, but it shouldn't cause too much of a disruption. Okay. So last time we learned about white dwarfs, right? And we learned about white dwarfs as the death of low mass stars. That was our discussion. What is a white dwarf primarily made out of? Why don't you guys make me feel good about not giving you a final exam by enlightening me and showing me all that you've learned from these lectures? Carbon, says a Runsack. Excellent. So they produce a white dwarf. And a white dwarf is primarily made out of carbon. Now, because a white dwarf is not a star, it does not have fusion. Typically what happens to white dwarfs is they radiate away their energy and they cool off over time, probably eventually becoming a dark carbon cinder floating in the inky void of space. Let's look at an HR diagram and remind ourselves, oops, I did something weird here. Let's remind ourselves where we find these white dwarfs on an HR diagram. Sorry, it's taking a second to load everything here. Okay. If you guys can see my screen on slide 66, you guys will notice that white dwarfs are found down here in the lower left quadrant of the Hertzsprung-Russell diagram. And that means we can immediately evaluate some of their properties. Are these things luminous or are they dim? Could someone please help me evaluate the graphical data? Are white dwarfs brighter than stars or dimmer than other stars?
Dim.
They're dim. How about their temperatures?
Cold,
No.
hotter.
No, they're warm.
They're extremely hot. Remember that white dwarfs are basically the exposed nuclear or former nuclear cores of a low mass star. It's as if you ripped the heart out of a star and then exposed it to space. Because that heart was once the nuclear furnace of a star, they're extremely hot, at least for a while. Caitlin, you might have been confused because I said they radiate and cool off over time. Over time, the reason why they're on this diagonal is as they shine away their light, they slowly decrease their temperatures and eventually go dark. How about the radii of white dwarfs?
Small.
Very small. In fact, we learned that they typically have radii the size of planet Earth, right? And over time, there must be, I think this is going to be part of our homework this week. If you think about it, every time small beans, these things must litter the galaxy, just burned out carbon husks, degenerate carbon husks floating in space. That must be really weird if you come across such a thing. Today, this week, we talk about the death of high mass stars, okay? So let's get into, well, actually, I want to remind you guys of one other thing, that white dwarfs can sometimes be found in a configuration called the high mass transfer binary. And I'm going to be making a big deal about this later on because we find transfer binaries including white dwarfs as well as other things. Remember that because a white dwarf is packing something close to the mass of the sun into a small nugget, these things do have considerable gravity. And in those instances, which we know are common, in which a binary pair is present with a white dwarf, the star that eventually becomes a red giant in a companion with the white dwarf can swell to such immense sizes that the gas that makes up the outer envelope of the star can sort of drift over and get captured by the white dwarf. And as that gas inspirals, the gas is collisional. It has a lot of friction. And this hot disk of gas will heat up to immense temperatures, sometimes radiating in the X-ray portion of the spectrum. That means their temperatures can get upwards of 30,000 Kelvin or something. Maybe it's time for some space art. We'll have to ask our weed-smoking artist friends, accretion disk, to draw us a picture of an accretion disk. Now, we know that they can surround black holes, neutron stars, and white dwarfs. but I was hoping, of course, the first pictures that come up are always the supermassive black hole. So I guess I was hoping, here's some space art right here. I could go along with this. All right, so something like this is what it would look like if you could travel in your Starship Enterprise and go visit one of these on a science mission, then you would be able to see something like this. Unfortunately, our telescopes do not have sufficient resolution to resolve these disks, although that's actually not true anymore. As you guys know, a team a year ago took the first, actually it was sort of a collaboration of radio telescopes around the world, took the first ever image of a supermassive black hole. And that was probably the first time we've ever directly imaged an accretion disk. Because the black hole was so massive, and the accretion disk was so large, we were actually able to get our first sort of low resolution bona fide picture. Now, this might not look like much to you, but this is more than I ever got when I was a student. What the crap is going on here? All right, you can actually see the event horizon. We'll talk about this later when we do black hole stuff, but I got excited here. Sorry, I'm trying to manipulate Zoom and the internet at the same time. It's not easy. Okay, so today we focus on high mass star death. Let's do some note taking. High mass stars are more complicated. First of all, what constitutes a high mass star? That's something I expect you all to know about as part of this discussion. How massive should a high mass star be?
At least 8 solar masses.
Correct. And since they don't really get too much more than 100, we expect 8 all the way up to, we have detected a few stars with over 100 solar masses, but they're extremely rare. So first, the stage they go through, they have a sort of, like all of their stars, they have a protostar phase. And then they eventually become a main sequence star. And you'll remember that when a star is a main sequence star, that's like when it first forms and starts undergoing its fusion cycle. They undergo hydrogen to helium fusion in a different reaction cycle, in a different method than low mass stars. Now, this is asking you to remember something from a few weeks ago. Does anyone remember the name of the nuclear reaction sequence that high mass stars use to fuse hydrogen into helium? It is not the proton-proton chain. It's a different one.
The triple alpha.
Unfortunately, that's going to be our next stage when it becomes a blue supergiant or a red giant, whatever you want to call it. At those stages, then they can fuse helium. That's helium fusion. But I'm talking about hydrogen fusion, Christopher. In fact, we spent more time talking about the triple alpha process at this point than the reaction that I'm talking about. Anyone can name it before I get to it? Well, shucks. I guess maybe it's a good thing we ain't taking that final exam after all, right? Because I'd be asking you these kinds of questions on the final. This is exactly what the final would be about. The name of the reaction cycle is called the CNO cycle, carbon, nitrogen, oxygen, which is kind of weird because although they are used as ingredients in the reaction, they are not the purpose of the reaction. They are just sort of intermediary stages. Now, I walked you through this before. Guess I ought to do it again because you can't remember. But it starts off with a little bit of carbon somewhere in the nucleus of the star, and the carbon gets whacked with a hydrogen, and the hydrogen sticks to it and transforms it into nitrogen. Then another hydrogen slams into the nucleus, transforming it to another isotope of hydrogen. And then another hydrogen slams into it, and then another hydrogen slams into it. two of the hydrogen nuclei end up transforming into neutrons. The other two remain as protons. And right at the last moment, when the fourth hydrogen hits and it's about to turn into oxygen 16, instead, the nucleus splits apart, separating it into the original carbon 12, which is where we started, and it ejects a helium nucleus, also known as an alpha particle. Basically, the four protons use the carbon nucleus as a sort of nuclear tiki bar where they can get together and have drinks and then take off and leave the bar afterwards. Okay, so the helium, the four protons are using the hydrogen just to kind of get together, and then they take off. You'll notice that the net reaction, which is what we want to be conscious of, is similar to the proton-proton chain. Four protons transform into a helium nucleus. There's associated neutrinos and positrons that come out, and they go diddling their way through the star until the positrons interact with electrons, and the neutrinos fly right through the star and leave into outer space. But the energy produced is in the form of 1, 2, 3 gamma rays. You'll remember I had a whole spiel with y'all about how 3 gamma rays is a 50% increase in energy yield per reaction. And this is why these high mass stars shine so immensely. This is why their luminosities can be billions of times greater than the lowest mass stars. Okay, so like a low mass star, basically, or let's take this as a note. Hydrogen to helium fusion uses the CNO cycle. And the CNO cycle, it basically, it runs through its fusion quite quickly, sometimes in a matter of 10 million years, which is a very short time scale compared to our sun, which can burn its hydrogen for 10 billion years. At some point, depending on the mass of the star, the star will run out of nuclear fusion, and it will begin to evolve into something that's like a red giant. But sometimes these things are still so bright and hot and blue that they'll sort of enter a phase that's something like red giant, but it's probably more like a blue supergiant. And with the help of the HR diagram, I'm going to show you how a blue supergiant differs from a red giant. You kind of have to use the HR diagram to understand how a star is evolving. And I want to compare pictures 93 to the picture of our sun during its the low mass star evolution into a red giant. So let's remember what we talked about last week. Last week, we discovered that a low mass star has a hydrogen burning shell with an inert helium nugget. And then the star slowly starts to turn into a subgiant where its radius starts to grow and the star becomes big and fat and red, eventually turning on helium fusion, turning into a sort of variable helium burning star, and then eventually turning into a double shell red giant. And so it's kind of evolving in this direction. They call this the asymptotic red giant branch. And that just means the sun is growing to immense radius and swallowing up some planets and such. Unlike low mass stars, which kind of go up in vertical, supergiant or blue supergiant stars like O and B type stars, they tend to kind of drift horizontally to the right, which actually does imply a small increase in radius, because remember that radii kind of go along a direction like so. And if you're drifting to the right, you are actually increasing your radius a bit. But mostly what's happening as their radii get bigger, they get a little bit cooler, but they're still blue. So let's just go to slide 93. And let's just ask a couple of questions to make sure you guys are following me here. Let's choose a particular star, like this blue giant here. And we're watching as it evolves into its next stage of life. What's happening to the temperature of the star? These are supposed to be easy softballs. Could you just answer like with your voice instead of making me go into the stupid chat log? It also is annoying for the night student. It's cooling down. Yes, thank you. The luminosity?
Going up.
False. Do better.
Going down.
False. Do better.
Stays the same.
Exactly. We can see that the luminosity has not changed because they are not drifting up or down the y-axis. What's happening to the radius?
It gets bigger.
Yes. Oh, wait a minute. How can the luminosity not be changing? It's getting bigger, but its temperature is dropping. Let's think. What does that mean? I guess according to the Stefan-Boltzmann law for stars, if the luminosity is constant, I can remember that the luminosity of a star goes as its radius squared times its temperature to the fourth power. So it must be that the temperature is dropping by one amount and the radius is going up by just the proper amount such that the two balance each other out, and the star's getting cooler, but because it's getting bigger, it's got more panels to shine away light. So that's kind of interesting how that's happening. One thing I've read from my graduate books is, unlike low mass stars, which have to first swell and compress their insides in order to build up enough temperature for helium fusion, these guys are so hot in their interiors that as soon as the hydrogen is done, there's just a gradual transition to helium fusion. So once they start going into their blue supergiant phase, and let's just call them, let's call them blue supergiants, okay? They undergo helium to carbon fusion basically by the same mechanism that low mass stars do, by the triple alpha process. And that kicks in somewhere around a temperature of 100 million Kelvin. For a low mass star, carbon is the last element that can be fused. Not so much for a high mass star. High mass stars, so let's just remember that probably some people forgot the triple alpha process. No big deal, it's really simple. 3 helium nuclei smashed together to make carbon. Couldn't be any simpler. Remember that even though it produces 1-2 gamma rays per reaction, the cost is a lot more mass has to be input. So a star cannot fuse helium to carbon for as long as it can fuse hydrogen to helium. Low mass stars only live on the main sequence for 10 million years. It must be like, I don't know, like probably under 1 million years for it to undergo helium to carbon fusion. Unlike low mass stars who can never get hot enough to fuse carbon, high mass stars do. And they begin afterwards, after their carbon is formed, to go through a set of more intense nuclear reactions that build up what are basically all of the cool, heavy elements in the universe that our planet and our bodies are made out of. So all the stuff that we hold dear is made out of the next cycles of reactions. I'd like to show you a couple of them. The first thing that happens is something called helium capture reactions. Function F5. Oh, hold on. Function F5, slide 100. So we start just smashing together all kinds of different nuclei in a smorgasbord of nuclear fusion. Carbon gets whacked by a helium nucleus so violently that they stick together and they form oxygen-16. This is what was supposed to happen in the CNO cycle. Then your oxygen-16 will get whacked by a helium nucleus, so violently that they'll fuse together to make neon. Neon is a noble gas. Neon is then whacked by another helium to form the element magnesium, 12 protons and 12 neutrons. They call it helium capture because everybody just starts getting hit in the head with a helium nucleus, okay? And they start fusing 2 by 2, just like Noah's Ark there, you biblical fans. 2 by 2, these nuclei increase until they become heavier elements. You know, one of the curious things about the cosmic abundance, I'm probably talking about stuff you guys can't remember, but you might remember that there's this list of how abundant the elements in the universe are. And it's known to astronomers as the cosmic abundance of the elements. And I'd like to point out something that you probably didn't notice the first time I showed it to you. Okay. There is a crazy madman shouting on the streets, and it's distracting me a little bit. Hey, guys, if you can remember 5 seconds ago to what I was talking about, can you explain what the helium capture reactions have to do with this little zigzag? You will notice that there's a difference in the relative abundance of elements. Up, down, up, down, up, down. The universe contains more neon than sodium, more magnesium than aluminum, more silicon than phosphorus, more sulfur than chlorine, more argon than potassium. Can you tell me about that zigzag pattern? And what that's got to do with Noah's Ark?
The thing where the helium is like fusing with the other things. It's going like the 2 by 2, you said. So that means some like don't get produced as much as others then, right?
And which nuclei will be favored, Christopher, using that logic? The nuclei which will be favored are the, fill in the blank here. Is there anyone out there who understands what I'm talking about? All right, I'm desperate. I'm going to the chat log. Christopher, yes. Hell yeah, creating neon. Which nuclei will we find in greater abundance? Let's see. Oxygen has 8 protons. Neon has 10 protons. Magnesium has 12 protons, I think.
Even numbered one?
Yes. Even numbered nuclei are more abundant than odd numbered nuclei because fusion in high mass stars at first proceeds by helium nuclei slamming into things. Remember, it's interesting that our DNA, deoxyribonucleic acid, is made up of carbon, nitrogen, oxygen, and phosphorus. These are still some of the most abundant elements in the universe if you ignore hydrogen and helium. Potential for aliens, very high. Okay, very high. If you keep mixing those things together in high temperatures, sooner or later you're going to create some complex chemistry. Okay, so first we've made some cool heavy atoms, and then you know what happens? High mass stars don't stop there. They are so massive, their internal temperatures are so shitty bonkers that they eventually just start slamming the high numbered nuclei together in something. There's more advanced names in other books, but your book calls them heavy element reactions or other reactions, something kind of lame. But let's just kind of take a look at some of the more popular ones. Oxygen 16 smashes into carbon 12. Oxygen 16s slam together to make sulfur. Silicon slams into silicon to create iron. But my friends, at iron, that's where the buck stops, okay? Iron is something that we call in nuclear physics a magic nucleus. There's a reason why the centers of planets are made out of iron. Iron turns out to be this special kind of nucleus where, okay, let's remember what glue, actually, that could be a thought question for you guys. What is the force of nature that is responsible for holding the nucleus of an atom together? What holds all of these protons in place?
Is it the strong nuclear force?
Excellent, Christopher. And the strong nuclear force works by kind of like pairing a proton with a neutron, and their quarks kind of glue themselves together. The thing is, Christopher, the strong nuclear force is a short range force that is very, very strong when you're about a proton diameter. Oh, that's my guest. Daddy's not drinking alone tonight. Okay, so so you're binding the proton and the neutron together, but over a short range. Now, here's what's interesting. An iron nucleus starts to get so big and fat. I mean, let's think about it. You got 26 protons, and protons, oh yeah. You know, I'm taking this little chance. I know COVID's gotten so out of control. I talked about this with the students yesterday. Are you guys freaked out? Do you realize that, let's break the fourth wall for a second. Rhode Island is now #1 in COVID infections. So that's pretty intense, right? Are you guys all going a little crazy? Yeah, we're #1 per capita.
For 100. State, too, that's absolute.
Yeah. So I am taking a risk by having my ex-girlfriend come to visit, but we've both been in isolation, and we need drinking buddies.
Fall River CCRI actually lost a professor due to COVID.
Really?
Yeah, the robotics and 3D printmaking teacher.
No, I know that person because he was in my department, but he actually died in a rollover. So I don't think it was COVID, or maybe they're
at least what's the email said from CCRI when I got it today.
Oh, today?
That's why I was looking at it. Yeah.
Huh. Hi, welcome. Make yourself at home. Did I get that email as well? You know what's really sad about Paul Sardina is he was an adjunct in the physics department where I work, and he was a very nice guy, and he taught like the rapid prototyping class. This summer, I wanted to make a model of Tycho crater, and he took a day out of his life to make me this. I was looking at it last night. I had data from NASA on the elevation structure of a legendary crater on the moon called Tycho crater. And I had these, I didn't have any 3D rapid prototyping equipment, but I knew he did. And I asked him if he'd be willing to print out one of these models. And it took him a whole day to do it. And I never got to thank him for that before he passed away. And so this is a little, every time I look at this, I'm going to think of that guy as a little keepsake. So it was very sweet, very nice of him to make this for me. So, well, you have to take my 1010 class, and that requires an extra $550 for me to tell you about the central peak. I'm just kidding. So in my astronomy 1010 class, we learned about crater formation. And this little mountain is called a central peak. And basically the force of the impactor is so violent that it liquefies the rock, and it becomes like a splashing of a stone into a pond. And that's the slapback of the liquefied rock recoiling from the impact, but then it freezes in the vacuum of space and turns into a little mountain. So if you look at craters on the moon with a simple telescope, you'll notice that about half of them have this central peak in the center. And I just thought it would be a cool thing to have a printout of. By the
You
way,
see that sometimes on Earth craters as well, I think.
Yes, they do. That is correct. By the way, although I use it more for my 1010 class, I have a fragment of a meteorite here. I wish you guys could hold this because it's incredibly heavy. All right, and this was part of the. I am not reading out loud what Runsack just typed into the chat log. Okay, I like my job. I want to keep my job. Okay, so This fragment of a meteorite, that's a good question. This fragment of a meteorite comes from legendary Meteor Crater in Arizona, where I've been to, and it's made of iron. And why is that interesting? Because this lump of iron I'm holding in my hands, this dense iron, was forged in the nuclear furnace of a high mass star. This is you've been to Barringer, Cameron? Holy kid, no way. So I got to tell you guys, if you want to hear some more personal anecdotes, when I was in college, you know, I'm a Rhode Islander like many of you are, and I went to Arizona because it's a good place to study astronomy. But I think my sophomore year, you know, I'd only been there for a year or two. I didn't have a ton of friends. And my father called me up and said, "Hey, Brendan, I've never been out to the West. Do you want to like just take the spring break and we'll go on a road trip together?" And I said, "Sure." It was one of the most memorable road trips of my life. He, of course, had planned out all these fun secret things for us to do. We traveled all around Arizona for a week. And one of the things that we got to do is, and Cameron knows about it because he's telling me that he's been, is we took a trip to Meteor Crater in the eastern Badlands of Arizona. And you got to understand, this impact crater site is about a mile in diameter, okay? Here's a picture of it, an aerial photograph. Let's see if we can find one. Okay, when you stand at the edge of this thing, you are awestruck with the violence of what this collision must have been like. I think it's, you know, maybe 10, maybe 30, 40 million years old. Weirdly enough, Meteor Crater is actually located on private property on a dude ranch. It's called the Barringer Meteor Crater. So to go visit it after you drive for hours and hours to the desert, you have to like pay $20 and they make you walk through this like tacky gift shop with I Love Alien keychains and UFO things and stuff. And then at the end, you can stand out in the observation deck and you can look out over this thing. And it's absolutely spellbinding. If you ever get out to Arizona, I'd recommend. You don't get to see craters like this every day on Earth, but if I start talking too much about this, I'm gonna start giving you my 10/10 spiel, and you got to sign up for that class next, okay? Anyways, to bring it back to the cosmic furnaces of stars, this lump of iron is made of the same nuclei that were forged inside of one of those high mass stars. And the way I got on this riff is I was telling you guys that while the strong force normally binds these nuclei together, something happens with iron where the nucleus starts to become so big that the strong force cannot effectively glue the protons together. And that means you can make elements heavier than iron, but instead of releasing energy through fusion, you actually have to put energy into the reaction. And this is part of something that we call the nuclear binding curve. This is a big part of understanding nuclear physics. I'd like to show you another graph because I know you love graphs. Something called the nuclear binding curve, which basically shows you which elements can undergo fusion and which elements can undergo fission. And I'm trying to find a nice, cute picture here. This one's pretty cute. Believe it or not, this is very intimately related to what we have to talk about in our class today. So what this is it's a plot of how heavy your nucleus is, your atomic number. All right, first of all, the mass number is what they're giving you here. That's the number of nucleons, but it correlates to the atomic number. And here it tells you how much energy is released when you go from hydrogen to helium and so forth and so on. So to fuse hydrogen into helium releases quite a bit of energy. To fuse helium into carbon per nucleon, as I mentioned earlier, you get less energy per mass. To go from carbon to oxygen, you get even less. But when you get to iron, iron is at the peak of the nuclear binding curve. These elements can release energy through fusion. These elements release energy through fission. Okay, prove to me that you understand my words. What's the difference between fusion and fission? Can you do that? Can anyone tell me the difference between fusion and fission? Simple, basic question.
Fusion is when they like bind together,
Correct.
and fission is when they pull apart.
Exactly. Just that simple, Caitlin. Thank you. So in other words, and I'm building up to something here, so work with me for a second. You can create elements heavier than iron. Let us review the periodic table of elements. Iron is not the most massive element by far in the periodic table. I mean, look at this bloody thing. F5, 16. Ah, nuts. Iron is here. Look at all those elements that are heavier than iron. There's like a lot of them. And these are elements that you're familiar with, like gold and silver and protactinium. Okay, so you don't know about protactinium, but you know about gold and silver and mercury, and you've heard about copper and zinc, and maybe you've heard of iodine. Those are things that we've heard about before, right? Those elements can also be created in stars, but as Caitlin points out, you don't get energy released. It costs you energy. If you try to smush an iron into another atom to turn it into something heavier like zinc, it will actually suck gamma rays out of the center of your star. Let's take a look at what the interior of a high mass star will look like as it nears the complete end of its fusion life cycle. Here's a lovely photo showing you what the interior of a blue supergiant might look like towards the end of its life cycle. It has an outer envelope, which is the radiation zone, basically. And then somewhere in the center is the core of the star, which we've expanded upon over here. And what you see is what I like to call the Tootsie Roll layering of a star, where you get a whole sequence of shells of different flavors of fusion. First, you have a shell that's undergoing hydrogen to helium fusion, then a shell that's undergoing helium to carbon fusion, then a layer of carbon that's fusing into other things like oxygen, oxygen fusing into neon, neon fusing into magnesium, magnesium into silicon, and eventually in the center, you get a lump of degenerate inert iron. A high mass star will not begin to fuse iron because one, it has incredibly high fusion temperature, and two, if you do start fusing iron, you will make the star unstable. Each of these fusion cycles has a time scale of roughly 1/100th of the time scale beforehand. And I want to play a little game with you to help you understand how fusion might proceed in a high mass star. And I'd like you to play along with me here to go through this. Let's title this part of your notes, Fusion Timescales in a High Mass Star. Okay. In the main sequence phase, the first phase of a star's life is to undergo hydrogen to helium fusion. According to our Hertzsprung-Russell diagram, shown in green, the time scale for such a fusion is, you can see it here, 10 to the 7 years, which basically means 10 million years. Each subsequent fusion, each new layer, the time scale will drop by a factor of 1 part in 100th, right? So let's ask ourselves about the next time scale. To fuse helium into carbon by the triple alpha process, how long will that time take if it's 100th of the time before it? Let's do some scientific notation together. You've got 10 to the 7 years, you drop it by a factor of 100, what do you have? Work them brains. Ten to the 5. How do you say 10 to the 5 years in plain English? $100,000. Good. Okay. The next stage is carbon fusing into oxygen. What's the time scale for that? Come on. This is easy stuff. I'm not asking you to do nuclear physics or anything. Yeah, it'll take 1,000 years, right? So the time will be 1,000 years. Cosmically speaking, that's a very short period of time. Now we're going to go from oxygen to neon. What's the time scale there? Thank you, 10 years. Now we're going to go from neon to magnesium. What's the time scale for that? How many years will it take to fuse all of the neon into magnesium? 1/10 of a year. How many days is that? What's 10% of a year in days?
36.525.
So is that Austin?
That's me.
Austin, and that was, hey, Austin, where's my PS5?
Listen, Professor, I told you that they're all sold out, but I'm working on getting you one.
You know, Cyberpunk is coming out, and we're all Jones in here. I've got some time to kill after this class ends, and I plan to kill it exquisitely. Okay.
That's only going to be on, that's a PS4 release until like early 2021, so you're good for a couple more months.
Oh, are you serious? Oh, I thought
you could play it on PS5, but the graphics won't be updated. It'll be the exact same thing, no matter which system you're playing on.
Never.
Hey, you could play it on PC on the 10th.
Professor,
that is a hot tip. That's a hot tip.
The PS4
Thanks.
disc that you buy, when you buy a PS5, it'll work on that, and it'll be the PS5 version too.
Okay, cool. Hey, that's actually a good tip. All right, hold on. So you said 37 days rounding up, right? Let's call it 36 days, just to make our math easier here. Doesn't really matter. Okay, after neon to magnesium fusion, we're doing magnesium to silicon fusion, right? And what's the time scale for magnesium to silicon fusion? Well, yeah, well, no. It's 100th a run sec. What's 100th of 36 days? Not 4 days, but 0.4 days, right? Does everyone understand how I got that? I moved the decimal place over 2 and then I rounded up. What's 40% of a day? How many hours is that? That's about 10 hours by my reckoning. And finally, silicon will fuse into iron. What's the time scale there? False. Man, someone doesn't know how to divide by 100, and that someone is you. What's 10 divided by 100?
0.1.
So how many minutes is that?
6?
Yeah, my graduate student books tell us 15 minutes. Wait, did we do that right? 10th of an hour times. Yeah. And that's when you're supposed to go, holy effing shite, okay? A run-sack, it's a teensy bit more complicated than that, but that gives you the flavor of the feeling. I'll tell you. So, okay, a run-sack wants to know, why is it so uniform? It has to do with the nuclear binding curve. A run-sack, you can see that every time I go from one element fusion to another element fusion, this release in energy per nucleon, this is how many mega electron volts of gamma rays do I get per proton or neutron. It keeps dropping in a logarithmic fashion. You keep losing, it costs you way more mass to release the same amount of energy. So the star just starts crunching through its matter faster and faster and faster. By the time the star has turned into a bunch of silicon in its nucleus, so let's get back to my slideshow for a second here. By the time this entire core is turned into silicon, it undergoes silicon to iron fusion on a time scale of about 10 minutes. And what do you think happens to the star then, when this turns into a hot, degenerate lump of iron? Remember, if iron starts fusing into any other element, it will suck gamma rays out of the core of your star. What's that mean for hydrostatic equilibrium? What's that mean for all of this 25, 30 solar masses worth of matter squeezing down on the core of your star? What happens then when the fusion runs out? Anyone know? Boom. A run-sack, that's right. Boom.
Supernova.
Yeah, it's called a supernova of type 2. And what happens is all these layers of the star immediately start falling down on top of the other layers, and they jam all of, how do I explain this? They jam down on the iron so harshly that it smushes the electrons into the iron nuclei and basically creates a big fat ball of nothing but neutrons. And then you get a violent explosion propelled by neutrinos, of all things, called a type 2 supernova. Now, I want to show you a picture here taken in the 1980s. This is a picture of a small dwarf galaxy which orbits the Milky Way. It's known as the Large Magellanic Cloud. And what you can see is an arrow pointing towards an ordinary blue supergiant star that no one had really paid much attention to before. It was just one out of maybe a billion stars that make up this small galaxy about 50,000 light years away from us. In 1987, this star underwent just such a supernova, and this is what it looks like a day later. There's your before and after. Try to understand that this light here at the center of the galaxy, this is the smeared out combined light of close to 1 billion stars. You will notice that the luminosity of this one high mass star, when it goes supernova, is comparable in intensity to the total collective luminosity of up to 1 billion stars. That's an immense explosion. And this supernova creates a very, very violent eruption. By the way, we've been imaging this thing ever since. That was 1987. Do you want to see what it looks like today? If you look at it, let's go to the internet, and if we just type in supernova 1987A, this is what it looks like today. If you look right at the heart of where it is, isn't that cool? Let me walk you through this. This is a ring of ionized gas expanding out from some central nugget with these two beautiful sort of magnetic plasma rings surrounding it. It might be helpful to have a weed smoking artist illustrate this for us so we can understand just what we're looking at there. This is probably what it would look like if you could get a little bit closer and a little bit higher resolution. You're witnessing the birth of something that we call a supernova remnant. A supernova remnant is the equivalent of a planetary nebula for a high mass star. But unlike planetary nebulas, which are usually quite symmetrical and pretty looking, supernova remnants are very violent, and the gas is often shredded. Probably the most famous example of a supernova remnant is the Crab Nebula, which is related to a supernova that Chinese astronomers observed in the year 1054 AD. And so that was, 1,000 years ago when this star went supernova. So it's had some time for the gas to propagate. And this is what eventually a high mass star supernova turns into. Here's a high resolution image of the Crab Nebula in all of its glory. Look at how this gas has just been sort of pulled apart like pulled pork sandwich or something. It's hot ionized gas. And these filaments of gas contain many of the heavy nuclei that we just stepped through. And this enriched gas, by the way, it's going to go back out into the galaxy's disk and eventually become part of another generation of star formation. And those stars will have little planets around them, and those little planets will have little bits of lumpy iron in their cores that were once fused inside of those stellar furnaces. Or seaweed. Yeah, it looks kind of like seaweed, Zach. I agree with you. Okay. Now it's time to talk about the degenerate husk, what's left behind, okay? So let's take some new notes. Everyone got the fusion timescales for high mass stars? I'm erasing. Okay, so a high mass star death this is going to get a little confusing because there's a couple of different directions for the roadmap to take. Basically, it leaves behind two parts. And it's somewhat similar to a low mass star. Low mass stars had a planetary nebula from the outer envelope, and they had a white dwarf in the center. The first part is a type 2 supernova remnant. And that's the thing that looks like the Crab Nebula. It's a bunch of sort of shredded gas or shredded seaweed, as Runsack said, okay? Some kind of big, giant filament of gas that's expanding into space, all right? And the other thing can be one of two things. The second thing is whatever is left behind in the center. And that's usually called the, well, they sometimes call this a remnant as well, but there are two options. For the central, what was once the central core of the star. Option number one is a neutron star. And usually the neutron star is what you get behind, what you get left behind. If the star was a high mass star, but this is going to sound kind of confusing, a lower mass high mass star. So if high mass stars go from sort of 8 to 100 solar masses, let's see, the core of a star can be like 25 to 50%. Let's say the core of the star is, just keep it simple. Let's say it's 25% of the mass of the star. Neutron stars themselves typically have a mass range of 1.5 solar masses. You'll remember that's just over the so-called Chandrasekhar mass limit, which I'm sure everyone's forgotten about, all the way up to somewhere around 3 solar mass units. So if we divide 3 by 25%, that's like multiplying by 4. I'd say anywhere from 8 to 12 solar mass units of star, these are going to give you a neutron star left behind. If your star is above 12 solar masses, your central core is going to be over 3 solar masses. And at that point, things just get really bizarre. That's when the central core of the star doesn't just compress into a ball of neutrons, it actually self-collapses forever into a black hole. So these are your two options. We'll deal with the neutron star first. We'll deal with the black hole afterwards. So this is 12 to 100 solar mass units. Students, if I compress a star into a ball of neutrons, do I have a good picture for this? Probably not. What is that neutron star made out of? Like, here's one hypothetical model of what a neutron star might look like. Basically, a neutron star is a giant ball of neutrons. What element would you say this thing is made out of? Oh, Cameron knew what the Chandrasekhar mass limit was. Very good. Is a neutron star made of iron? No. Is it made out of hydrogen or helium or beryllium or what? Why don't you guys finish these notes, because I want to start taking some notes on a neutron star. Kind of, Cameron. I'm going to erase this unless someone tells me to stop, okay? I'm erasing. Let's talk about neutron stars. If I had to draw a picture of a neutron star, I guess I would draw a sphere. And then I would make that sphere a bunch of highly compressed neutrons. So let's just, fill our sphere up with all these neutron jelly beans. And they're all packed uncomfortably close together. So close that the diameters of the neutrons, if that even makes any sense, are basically compressed up against each other. These objects, which are not stars, are basically a ball of neutrons. So a neutron star is a ball of neutrons. I would like to point out that we define elements in the periodic table by their atomic number. The atomic number, all right, look, I'm afraid to ask this question because I'm afraid that you guys aren't going to know the answer and then I'm going to want to die, okay? What does the atomic number of an atom tell us?
Where it is on the periodic table.
Where it is in the periodic table, or okay, or in other words,
how many protons it has.
How many protons it has. How many protons? No, the nucleons is the mass number. Catherine just got that one wrong too. she thought it was the weight. The mass number tells you.
Catherine, close enough.
Okay, the atomic number is technically 0. That means this is not any atom in the periodic table of the element. This is kind of like, in a weird way, it's basically a giant atomic nucleus. It's like taking the nucleus of an atom and supersizing it. While it might be giant by atomic nuclei standards, it's pretty freaking small by star standards. So the typical mass of a neutron star can be like maybe 1.5 to 2 solar masses, right? The radii of a typical neutron star, 10 kilometers. I'm pretty sure the city of Boston is only 5 kilometers across or so, or maybe it's 10 kilometers. I wonder what the dimensions of this. Can I get the city of Providence? Maybe they'll give us the dimensions in Wikipedia. That would be kind of cool. The dimensions in kilometers is what I want. Yeah. There we go. Okay, so it's 50 square kilometers. What's the square root of 50? Providence is about 7 kilometers. If Providence was a square, oh, you're back to Providence. All right, Austin, I'll be seeing you at Tallulah's Taqueria, okay? With the PS5 in your hands. Anyways, okay, 7 kilometers across this is comparable to the city of Providence. You've smushed 1.5 times the mass of the sun into a sphere the size of Providence, Rhode Island. That's pretty weird. And the whole thing is a giant atomic nucleus. It's held together not by any fusion forces. It's held by something called neutron degeneracy pressure. And that basically means it's the quantum states of the neutrons. They're obeying the Pauli exclusion principle. No two neutrons can have the exact same energy state. And it's sort of like the neutrons are pressed up against each other, providing the resisting force. Who knows what happens as you go down into the interior of this object? At some point, it might break down into a puddle of quarks, which is pretty wild to think about, right? I don't know if you guys remember this. I don't know if I actually ever told you this, but a neutron itself is comprised of 3 smaller particles called quarks. And neutrons have 2 down quarks and 1 up quark. And they're kind of all buzzing around each other. At some point, we hypothesize that the neutron itself might break down and the up and down quarks might actually get uncomfortably closely pressed together. I think what we should do is calculate the escape velocity of such a neutron star. So I want us to do a little math because these are the last 2 classes. So let's find the escape velocity of a neutron star. Okay. The escape velocity is the square root of 2 times big G times the mass of the star divided by the radius of the star in MKS units. So that means we have to do the square root of 2 times 7 times 10 to the minus 11 meters cubed per kilogram per second squared. Let's see. What's 1.5 times the mass of the sun? What's 1.5 times 2? Isn't that 3? Right? So it's 3 times 10 to the 30 kilograms. Hey, Runsack, what's 10 kilometers in meters? False. Elijah, what's 10 kilometers in meters? Y'all suck at metric system. Yes, 10,000. meters, right? Okay, punch them up for me. You can't get out of this class without a couple more calculations. One sig fig is fine. And yes, I want the answer in scientific notation. What are the units? I got time for you to figure out the units. That's meters per second. What is the speed of light? The speed of light is 3 times 10 to the 8 meters per second. What percentage of the speed of light is this number? That's right. This is 66% of the speed of light for the escape velocity. Does that meet our criterion for a relativistic object? Lovers of general relativity? Damn, exactly, Kim. False, Arunsak. 20% of the speed of light is considered relativistic regime. You are way the F over that. These are highly relativistic objects. I want you to write that down. Highly relativistic objects. That means time runs slower at the surface of a neutron star than it does in deep space. That means photons themselves have a hard time leaving the surface of the star. Even light gets messed up around a neutron star. Do you think we have any images of neutron stars?
No.
Hell no. At 10 kilometers, they would barely give off any light at all because of their small radii, but the light photons themselves are getting redshifted just trying to jump off the surface of the star. In fact, these things are teetering on the edge of collapse. If you push this to 2 or 3 solar mass units, you quickly hit the speed of light as your escape velocity, and that's it. Then you collapse into... They're almost invisible except for Cameron. Now, before the class ends, I'm going to tell you a cool yet horrible story. You guys will remember that when we looked at images of the sun in the X-rays, we could see that the sun was a powerfully magnetic object that has magnetic fields threading all throughout the plasma of the star. And there are stars that have much more powerful magnetic field activity than our own sun. Now, let me try this. The sun has a sort of potent magnetosphere surrounding it. I was just hoping we could find some kind of a cool image of the sun's magnetic field somewhere, or a depiction of the sun's magnetic field. Okay, so this is kind of what the magnetic field lines look like poking out of the sun. One of the things that you guys can remember from our discussion is that magnetic field lines, they get stuck to plasma. Plasma and magnetic field lines, they stick to each other. When a high mass star collapses down into a ball of neutrons, it's very likely that any magnetic field lines that are connected to the star, excuse me, are going to be pulled down towards the interior and enhanced as you bind all of the magnetic field lines together. And what happens is the collapse of a high mass star's core also causes extremely rapid rotations. And I want to talk about the first time we observed a neutron star. It wasn't directly through imaging. In 1967, Jocelyn Bell was an astrophysics graduate student working in the United Kingdom under a professor named Anthony Hewish. And they had built some of the world's earliest radio telescopes after World War II. Early radio telescopes didn't look like a big dish, but they almost looked like the kind of antenna that's popping off your grandpappy's house so we can watch the TV. They just looked like long rays of antennas where they were trying to pick up radio waves from space. As the graduate student, her job was to pick up and record radio data from space and try to analyze it. Jocelyn Bell discovered this small but extremely rapid and very uniform radio blip. It was a 33 millisecond beeping of radio waves, radio blip, radio blip, radio blip, flashing on and off 0.03 times, or with a period of 0.033 seconds. So every 33 milliseconds. That's incredibly rapid, right? That's faster than you can blink your eye. The pulsation period of these radio waves was so uniform that they first codenamed this project LGM, which stood for Little Green Men. They literally thought that only an advanced alien species could send radio pulses with such a uniform and rapid periodicity. They thought they were looking at a blinking beacon from some extraterrestrial aliens. They couldn't figure out what to make of it. Now, apparently, Jocelyn had learned about this possible theory that when neutron stars form, when they collapse, that they might drag radio magnetic fields along with them, and those magnetic fields could eject plasma particles that give off light in the radio portion of the spectrum. In other words, she sort of worked out this theory of something called a pulsar. And a pulsar would be a stupidly fast rotating neutron star in which the magnetic axis was misaligned with the rotation axis. And keep in mind, that's how it works for planet Earth, right? Magnetic north differs from geographical north by about 12 degrees. In this case, the rapid rotation of the pulsar could cause the radio beam to occasionally flash towards Earth. And she basically used these rapid pulsations in the radio spectrum to argue that she had detected the world's first neutron star by measuring radio pulses from a pulsar. And for that discovery, her advisor was awarded the Nobel Prize in Physics. So he took all of their work and research, and he basically got all the credit for it, and he won the Nobel Prize in Physics. Now, she gave a talk here about a year ago, right before COVID hit, and she claims she's not bitter about it. She, well, of course, went on to become a very famous astrophysicist in her own right. But yeah, some people think of it as a dick move. You know, if you ever become grad students yourself, make sure that you're, you hold on to your data and make sure it's a true collaboration. In any case, my point is that today, it is possible for us to observe neutron stars indirectly by detecting their radio bursts from their magnetic axis. And this is my last note for the day before we take a pause. These are called pulsars. So a pulsar is a rapidly rotating neutron star with a powerful magnetic jet, and they can be observed in the radio regime of the electromagnetic spectrum. So we can use radio telescopes to discover. Famously, the pulsar that she observed, guess where it was eventually discovered to be located? Right in the heart of the Crab Nebula. Does that make sense? That Jocelyn Bell's 33 millisecond pulsar would be discovered? Yes, Arunsek. Why does that make sense? That it would be found in the heart of the Crab Nebula. That's right. It's the leftover core of that high mass star that exploded. So pretty wild stuff. Okay. We've burned up another hour and a half. This was our penultimate class. We only have one class left after this. Since we're not taking an exam, we are going to do a lab today and homework. I got to tell you guys, today's lab was supposed to be a galaxy-based lab, although it involves studying star clusters. I've only done this lab once, so I don't know how smooth it's going to be, but I thought maybe the chaos of it all would be part of the fun. We'll see if it's fun. Hopefully it's short. I haven't done this in years. Why don't you go ahead and print out, I put it up last night under lab. Come on, baby. Let's get rid of some of these tabs and okay. I hate you, Blackboard. Lab. Here we go. You have to print out two things because there's this PDF and there's this PDF, which is a graph that we need. So if you could print out both, that would be helpful. All right, I'm going to take a little, 15 or 20 minute snack break, and I'll hit print on those things. And then we'll get back together and we'll try to do this lab as quickly as possible. Sound like a good idea? All right, I'll see you guys in a bit. I just realized that I forgot to start the recording. So my description of what we're doing today in lab got cut off. The idea is that we're going to hunt for the center of the galaxy by studying some properties of globular clusters. Now, I don't want to go into that whole spiel again because I'll bore the people that I'm talking to, but night students, just follow along as best you can. We're going to need the printout for today's lab, including that extra sheet, which is figure 25-5, and that's going to show us a bunch of globular clusters distributed around some location. And as I was saying to the class, Harlow Shapley discovered the center of the galaxy by basically measuring the distances from the sun to a number of well-known globular clusters, and then trying to figure out where the globular clusters were distributed about and what the center of all the globular clusters are. Basically, he said, the center of the galaxy should not be the center of the observable stars. The center of the galaxy should be the center of the globular clusters, okay? Arensak says, if I don't have that sheet, would I be able to do the lab? Well, Arensak, you have a computer in front of you, yes? You can use MS Paint or something to notate this on the page itself, right? So we did this before with some of our labs. I was thinking that perhaps you could just call up the sheets, right? And then you can use like one of these tools to just mark right on it. I don't know. Yeah. Oops. You can type here and you can make circles, and I think you can even write. Can't we draw on this thing? I remember doing that once. Or we might have to open this up in MS Paint or something. Can you figure that out? What about opening up with Microsoft Paint? Can you do that? Or whatever image program you have? Austin, tomato sandwiches are not strange. A tomato sandwich is the most sublime thing you could ever possibly imagine. You just take 2 pieces of bread, you put mayo on it, you slice tomato, and you cover it in salt and pepper. I'm telling you, my father taught me this. It is the most exquisite sandwich. It's very quick to make. Try it sometime. All right, they're not buying it. Okay. Mayo should exist solely for the purpose of tomato sandwiches. Tomato, mayo, salt, and pepper. Oh, godly combination. Okay. Okay, so let's give this a shot. Arunsek, can you figure out something where you're able to draw on that? Have you worked on that? Okay. Let's get into it. I'm going to try to go into phone mode here. Okay. Wi-Fi. Let's see if I can do this without embarrassing myself. Caitlin, can you figure this out as well? Do you guys have a strategy? You don't have a strategy, Caitlin? Okay, let me suggest, all right, hold on. Let me suggest something here that download the file. Let's start there, okay? Let's see if I could figure this out. I'm gonna try to open this up. Oh, choose another app. Choose another app. I want Paint. Let's see if this works. Fudge. Okay.
So what I do is I take a screenshot of it and then just paste it into whatever.
Into Paint.
Yeah, or my
I don't want to
drawing
assume that everyone
program.
has Photoshop. I just have Acrobat. I thought there was a way to draw on things with Acrobat Reader. You just take a screenshot of it. How do you screenshot it? Just with print screen? I never screenshot it.
Yeah, print screen.
And that copies it, and then you paste it into Paint.
Yeah.
Is it possible to draw on a PDF with Reader? You can sign it. All right, that's too lame. I can't. That's not a drawing tool. Okay. What you're going to do is, do you see here, Caitlin and Arunsek? You can open this up in Adobe Reader. Why don't you just do this? Just type stuff in, right? Like 45, whatever. You can at least do that, correct? Using this tool. Do you see that, Caitlin? Wait, Caitlin, you must have Acrobat Reader on your computer, correct? Can you unmute so I can hear you? I'm just having a hard time communicating with you.
I was trying to full screen my screen again so I could see what you were doing, but it doesn't want to work for me, so never mind.
All right, so Caitlin, did you download, let me just start by asking a series of simple questions. Did you download the files?
Yeah.
Okay, when you open them up, do they open up in Acrobat Reader?
No.
What do they open in?
A PDF.
Well, what PDF? A PDF must be read by some program. So what program is it opening in? Can you see my screen right now? Look at the top. Do you see that little thing there? That means Acrobat Reader, Adobe Acrobat Reader. Is that what it says on your screen?
Wait, hold on. I can't like zoom in on this anymore, and I don't know why. What's going on? Oh my God. I don't even know what's going on anymore now.
Caitlin, if you can open a PDF, the default program is usually Acrobat Reader. Sometimes people have weirder ones like Foxit or something, but normally it's PDF, Adobe Acrobat Reader.
Okay,
Arunsek, is that what you have?
No, it's not in Adobe Acrobat. It's not in.
What is it in?
I don't know.
But you can
You're
open it.
asking- Yeah, I can open it.
So look, just go to Help. And then it'll say about whatever the fuck this program is. Note to self, edit that out later.
Where's Help?
Usually there's like a menu. Are you using a PC? Or
I'm
Mac?
using a laptop.
Wait, is it
an HP.
Apple? Oh, it's an HP.
An
Okay.
HP.
So you're using a PC. So when you open up the file, there should be file, edit, view, window, help, something like that. At the
No.
top?
It's probably just opening up to her browser. So like
Yeah,
sometimes like
I think that's what it's doing. It's just
like to
opening
Internet
it up
Explorer
in
or
the
Chrome.
browser.
Yeah.
All right, thank you, whoever you are. Look, so when I said download, I meant download. So I see
I
what's
have
going.
it downloaded.
No, when you download it, it still will open up. If that's your default open, like it'll open to like
Yeah.
Chrome or something like that.
Okay, so
What-
what's the
do you-
simplest solution?
Do you have Paint, Caitlin? Do you have Paint?
I don't even.
You have to have Paint. Just go to your search bar and type paint, just like I'm doing
That's
here.
what I'm
Ready?
doing.
Paint. Boom. And then Christopher has the right idea. Screenshot, paste it into Paint, draw with Paint. Easy peasy guy. I should have just gone with Christopher. That's the right idea. Okay. Let's see if we can kind of get started here. So what they want us to do is they want us to look at a bunch of globular clusters. I think I'm going to try to switch to phone mode. Hopefully this won't be open with Microsoft Edge, says Arunsec. Oh, by the way, guys, there are some tools that you can access as part of the CCRI thing. That's right, I forgot about this. If you are at your CCRI home page here, if you are like in your email, do you see these 9 dots? You can click on the 9 dots and you can use different applications. And there's probably one that would let us draw on things. Like whiteboard or something. I don't know. Just try to figure it out. I'm going to switch to phone mode in hopes that this goes a little smoother. Let's see if that works. Share screen, iPhone. It's making me install a plugin again for some reason. Okay. All right. There we go. Okay, let's put our name up here. This is lab number 12. And I guess we can put the date on here. What is it, 12/7 maybe? And our section is AS1020 and whatever your section is, 001 or whatever, okay? Okay, finding the distances to a sample of variable stars. Figure 25.3 shows light curves of 6 stars out of a total of 45 observed by astrophysicists in the globular cluster M15. Okay, these are visual band filters. So what we can see here is this is the magnitude as a function of phase. And that's basically like a period of pulsation. Oh, these must be variable stars. These are RR Lyrae. So this is similar to what we did last time. RR Lyrae stars are another type of variable star, like a Cepheid variable. So we can see them getting brighter and dimmer, and brighter and dimmer, and brighter and dimmer. And I suspect what we're going to do is we're going to try to get their magnitudes and eventually their distances. So find the average magnitude of each star in figures 25.3 and 25.4 and fill in this table 25.1. So let's go to 25.3, which is this figure. And I'm just trying to figure out how we identify these. Okay, do you see right here this number? This is the star V17. And we need to find at V17 the brightest magnitude, the dimmest magnitude, and the average magnitude. So take a ruler and just kind of follow along with me. I'm going to hold this in a roll of tape. Okay, the way I'll find the brightest magnitude is I will do my best to go horizontal. And I will draw a horizontal line across at the top and a horizontal line at the bottom. I'm not going to do the smallest data point. I'm going to use the curve, okay? So what's that look like to you guys? This is 15.9. That's 15.5. How many boxes do we have in between? 1, 2, 3, 4. So what is each interval tick mark worth? Students, you know how to do this, right? What do we do? Okay, let me try rephrasing that question. I need to know what each little mini tick is worth. That's your job. How do I do that? What's the strategy that I've taught you guys before? I taught you a method.
Count like the number of ticks and then like, oh, fuck me. Like,
this is like basic skills for reading graphs. This is what this class should be all about. Arunsak's got it close. Arunsak, can you tell everyone how you did that? Because apparently your classmates need to learn, to remember what they learned.
All right, you take, is the music mad loud?
It's fine. We'll take something.
15.9 minus 15.5.
That's the interval, right?
Divided by the tick in between, which is 4.
Very good. Arunsak remembers that you take the interval and you divide by the number of boxes. So your interval, 15.9 minus 15.4, is 0.5 magnitudes. And we're going to divide that by 4 boxes. And that gives us 0.125 magnitudes per box. Wow, I wonder why it keeps 1 point. And by the way, 0.125 Arunsak is an eighth, right? That's how that works. That's why you shouldn't round it to 0.13, but keep 0.125, okay? Okay, so what do we think? This is 15.5. Let's add 15.5 plus 0.125. That's 15.625. And then, I don't know, plus 16.625 plus 0.125 divided by 4, maybe? So I'd say 15.66 is what I would get. You guys see how I did that? No? I argued in my head that that was roughly a quarter of a box. It's a little less than half anyways, right? Okay. So let's put down, I don't know how many sig figs we're supposed to use because I haven't done this before. So for V17 under brightest magnitude, I'm going to choose 15.66. What do you guys think is the dimmest magnitude? Oh, shoot. Holy smokes, guys. Look what I did wrong. The magnitudes get smaller as you go up, right? Because brighter stars have smaller magnitudes. I should have taken 15.5 and I should have subtracted 0.125. And then I sort of subtracted a quarter of 0.125. No one caught that, huh? Do you guys know what we're doing here? So let's do 15.5 minus 0.125. So 15.375 would be that tick mark. And let's subtract a quarter of 0.125 minus 0.125 divided by 4. That should be okay by order of operations. 15.34 should be the brightest magnitude. Don't we remember that magnitudes are brighter when they're smaller, correct? I almost made a major boo-boo. Okay, now watch what I do, because you're going to have to do this, okay? So we're going to take 15.9. I'm going to add 0.125. I'm going to add 0.125 again, and then I'm going to add half of 0.125. So 15.9 plus 0.125 plus 0.125 plus 0.125 divided by 2. 16.21. What's my average? Could you guys do something besides? I don't want to do this all. I want you guys to help me. What's the average?
I got a 15.78.
Excellent. Runsack, you are on my astronaut team. Okay. Hopefully the rest of these will go a little smoother. That was a little bit of a learning curve. We should check. It looks like they all have the same scale, or at least V18 has the same scale, right? 1, 2, 3, 4. Yeah, okay. So what would you say is the brightest magnitude? Ooh. It's a little bit above 15.5. I think 15.5 is there. This is a mess. It looks like it's on the very first tick mark. So 15.5 minus 0.125. That's my best guess. 15.5 minus 0.125. 15.38. What would you guys say is the dimmest magnitude? That should be easy to read.
I got a 15.65.
Okay, let's see if I get that same thing. I would have taken.
Oh wait, I'm adding it. Oops.
And you're adding it not once, but you're adding 0.125 twice, right?
I got 18.4.
18.4? Fuck no, that's not even on the chart.
16.15.
Is it 1.25 or?
0.125. We already.
Oh,
That's what we were doing, guys. A Runsack and I were busy solving this thing for you because we did the interval divided by the number of boxes. So I did 15.9 plus 0.125 plus
16.15.
Yeah. Is that what you got, a Runsack?
Yep.
All right,
Hey, Professor, is
Yeah.
it cool if I just turn in the chart because it's like impossible to do with the paint, or is it just really slow? Okay.
Yes. Yes. Just get something in. Anyway, you cut it. And then the average magnitude?
15.77.
Let's see if we can speed this up. I've got some bad news for you. It's, oh shoot. It's looking to me Sorry. I just want to get the auto lock done. All right. It looks to me like we've got a new scale here, doesn't it? We have to do the interval divided by the boxes again. That's 15.8. And I think that is 15.2, I think. So what's our interval? 0.6?
Yeah, it's negative 0.6.
And then how many boxes are there? 6?
I can't really, I counted 6, but it's hard for me to see.
1, 2, 3, 4, 5. I think it's 6.
Okay.
So I think here each one is 0.1 magnitudes per box. Okay, let's make sure we were doing that right. Yeah, I think so. Okay, so that's 0.01 magnitudes per box. So the top of the light curve is here, and the bottom of the light curve I'm going to try to bias it towards the tick marks to make our lives a little easier. If that's 15.2, 1, 2, 3 tick marks above means 15.2
Be
minus
14.9, right?
0.1 minus 0.1 minus 0.1. Yes, very good. 14.9. And let's add 15.8, 15.9, 16, 16.1, 16.2. Is that right?
16.2, yep.
And what's the average of those? $15.55. All right. All right. Oh, these graphs are a freaking mess. Okay. 16.0, 15.4, 1, 2, 3, 4, 5, 6. Each one is 0.1 again. Okay. So what's that? That's 15.4, 15.3, 15.2. Do you agree? Could someone keep me on task here?
Yeah, I'm following you.
16.1, 2, 3, 4. Let's take the average of those. 15.8.
Yep.
All right, cool. This is backing me up. V22. Ah, shit. We got to check our axes again. 15.7 and 15.2 is what? 0.5? 1, 2, 3, 4, 5. There's still 0.1 per tick mark, which is good. That makes me worried about this one. Why was this so weird? All of these have been 0.1, but these were 0.125. I don't know. Let's just go with what we have because I don't want to second guess myself at this point. So each of these are also 0.1. Okay. 15.2, 15.1. 15.7, 15.8, 15.9, 16.0, 16.1. Average them up.
15.6.
Okay, V23. Let's check our scale. 15.8, 15.4 is 0.4. 1, 2, 3, 4. So there's still 0.1, right? Do you guys follow that? Don't you think it's weird how all of these were 0.1, but these two are different? That's pretty bizarre, huh? Oh, well. All right. So anyways, these are still 0.1. What's the top one at? Why don't you guys read one for me? Should I get my pillow out or what? Would you guys be willing to read this and this for me, please?
You think the brightest one is 15.3?
Yes. What about the dimmest one?
Give me a second.
I'm not doing it. You guys have to do it. I give up. I quit. I quit because I'm bored and I'm tired and I just don't feel like doing anything anymore.
16.1.
Good. I agree. No, wait. No. Wait. Well, so Christopher, we can debate it, but I would say 15.8, 15.9, 16.0. Did you use the lower one? Is that it?
Yeah.
Let's go with Christopher's. What's the average? $15.7. Now we have to do RU106. Luckily, these graphs look a little bit easier to read. They all have the same scale. Thank God for that. Okay, class, how do I find the interval here?
It's 0.1.
Again, okay. That's 0.5, 1, 2, 3, 4, 5 boxes. Interval divided by the boxes. Okay. So what's our brightest magnitude? And what's our dimmest magnitude? I'm going to kind of bias it towards the tick marks.
And brightest is 17.1.
Yep. Dimmest magnitude?
18.1.
And the average should be 17.6 based on what we did before, right?
Yeah.
Okay, V10. Brightest. Let's cheat. I feel like cheating. Brightest and dimmest. Is it just me and Christopher? Give me a break. Come on. What do you, how many of you, I don't even know how many people are out there. Let me just look at all the trolls. Hey, Devin, Emily, Cole, Reardon, Daniel, and Austin. What the fuck are you guys doing? Nothing. Absolutely fucking nothing. You guys are just sitting back, taking it easy. I'm sweating it here, trying to figure out these magnitudes with Christopher, and y'all dragging on my science team.
Exactly.
I thought we were in this together, guys. I thought this was like 9 Musketeers or something. But it's 2 Musketeers and a bunch of slackers.
I'll play. I want to be a musketeer.
All right, okay, that's my point. Let's be Musketeers here.
Why
All
not?
right, all right, okay. I want to be a
Sorry.
Musketeer. That's okay. Like, I just don't know if you guys are following me. Like, why am I even doing this? Like, we could have just canceled lab. That thought occurred to me. Oh shoot! Now my phone isn't working. Okay, so why don't you keep going while I try to get my phone working? Give me the brightest and dimmest magnitude of V10.
Brightest is 17.3, and the dimmest is 18.
0.0. Right. Oh shoot. My phone thing isn't working anymore. Wait a second here. I should not have had to see. This slows things down when I have to chase you guys down.
I was here. Oh, I'm not muted. Just kidding.
All right. Okay. So why don't you get me V12 then, Stacy?
Of course. Okay.
I've got to reset my phone.
I'm gonna guess. I'm kind of blind here, but 17.5.
Fine. And
Right. 17.5 and I kind of want to stick with the 18.0.
yeah, I'll agree with that. Okay, Emily, get me V13. Emily, weren't you going to be a musketeer?
17.5 for the first one.
Okay, yep.
And maybe 17.9.
Yeah. Yeah, I was thinking that too. Guys, I'm still
Bless
fiddling
you.
with my phone here. I don't know what the hell's wrong with me. All this pepper, all this math, it's driving me crazy. Can someone get me V1? I'm trying to.
17.4 for the brightest, and 18.1 for the dimmest. Average is 17.7.
Okay, I haven't been getting my other
5.
notes. Wait, 17.75 is the average? Oh, here we go.
Yeah.
Okay, Christopher, do you have the averages of these other ones? Because I was fiddling with my phone here. So everyone else who's can copy this down.
How far back?
To V10 for me. Whoa, hold on. Okay.
V10's average is 17.65. V12, I got 17.8. Although my dimmest was different for that one.
What did you have for V12?
18.1.
It's somewhere in between the two. I'm going to go with 17.9. Wait, hold on. Wait, this is V12? Shit, what is this? You had 8. What did you have for your dimmest?
18.1.
Why don't we split the difference and make it 8? I'm going to make it 18.0. Which is 17.75 again, right? Yeah. Okay.
Wait, that was
right.
V13 you filled in.
Oh, shit. Oh, shit. Yeah, and that was 17.9. Thank you, Christopher. Jeez, what's wrong with me? 17.5 plus 17.9, 17.70. And then I'm just going to leave this as it is. Wait, 17.5 and 18.0 is 17.75. You can keep yours, Christopher. It doesn't matter. V5. The top one looks to me like 17.4, maybe. The bottom one,
I think 18.2.
fine. So let's get the average. $17.80. V6, 17.6 maybe.
Yeah.
The bottom is just
I think
barely
18.
18. What's that, 17.8? Is that
Yeah.
right?
Yeah.
Okay. The top here, 17.4, I guess.
I
It's
lean towards 17.3.
Okay, fine. I'll go with yours. 17.3. And then 17.
18.
Oh, you want to? Oh, you like to go the lower on the lower bound, huh? It's tough. I don't look. No way, no how. There's my line on 18. It's clearly below the stars. I'm going to say 17.9 here.
All right.
And that's 17.6, I guess, right?
I think so.
All right. Finally got all this. I love science.
I don't.
Well, what do you love? Do you love money?
Art, literature.
Let me tell you about art. Great way to turn yourself into a slave for a corporation. Am I right or what? Catherine's a visual artist and she's doing some work for a big company. Making lots of money doing it, by the way. So anyways, okay, now we've got to compute the distances. Because we have average values for the apparent magnitudes for each set of stars and a published absolute magnitude, so the absolute magnitude for all RR Lyrae stars is 0.59. We can use a version of the magnitude equation to solve for the distance in parsecs. Okay. Are these numbers, these page numbers listed here? Oh, we have to get the average apparent magnitude for M15. So I need some brave soul to add all of these 6 numbers up and divide by 6. Can you do that?
I already did it.
Oh, shit, yeah.
It's
You're,
15.70.
I'm loving you. That's great. Did anyone do it for R106? You are the best, Emily. You've earned
Also,
your
the next one is, I think it's 17.0.
Thanks. Remember, Emily, I'm looking at this almost like for the first time, like you guys are. So I'm kind of I thought part of this lab we would learn together. Okay. So now what we have to do is we have to put those into the distance modulus formula. So like for 15.7, our distance will be equal to 10 raised to the power of this shit. And this shit is 15.70 minus the absolute magnitude for RR Lyrae stars, 0.59 plus 5, and that's all in parentheses. And this is going to be kind of tough to write, divided by 5. So we're going to have to be very, very careful about how we enter this into our calculators. So let me put that there, and I'm going to watch me try to do it, and you guys keep track of me. Christopher's TI-85 might come in handy here, but let's try it. I'm going to do 10 raised to the power of open parentheses once, open parentheses twice. Now I'm going to do the top, 15.7 minus 0.59 plus 5. I'm going to close my first set of parentheses. Now I'm going to divide by 5. I'm going to close my second set of nested parentheses. And then I'm going to hit equals. 10,500 parsecs. I don't think we can choose more than 3 sig figs there. Wait a minute. I don't know which is the nearest and which is the farthest. So I'm going to write their answers down right now. Oh, by the way, guys, actually, I can tell you which is the nearest and the farthest. If the average apparent magnitude for M15 is 15.7 and the average apparent magnitude for R106 is 17, can you already tell me which one is going to be closer and which one's going to be farther?
The second one was 17.70.
Oh, apologies.
No problem.
Can you tell me which is closer and which is farther based on their apparent magnitudes? Guys, what should be the closer cluster? The brighter cluster or the dimmer cluster?
The brighter one?
That should be the closer one. So the 10,500 parsecs should be the brighter of the two clusters. You guys actually are following me better than I thought. Okay, let's try to calculate the distance here. The distance is 10 to the power of 17.7 minus 0.59 plus 5 divided by 5. So I'm going to add that up. Try this again. 10 raised to the power of open parentheses once, open parentheses twice. 17.7 minus 0.59 plus 5, close parentheses once, divided by 5, close parentheses twice, equals 26,400 parsecs. Wow, these things are far ass away. How many light years is that? It's about 3 light years per parsec. So if it's 25,000 parsecs, that's 75,000 light years away. That's how far these globular clusters are. The entire galaxy is 100,000 light years. So these are like outside the disk of the galaxy, right? Now we find the distance to the center of the Milky Way. Here's where we're going to use that crazy plot.
What are we going to do?
We're finding the distance to the center of the Milky Way galaxy next. So read along with me here. Figure 25.5 is a plot of 130 of the 150 known globular clusters that exist as part of the Milky Way. The globular clusters are indicated by the black dots. So each of these black dots is a globular cluster. Okay? This is where Earth or the sun is. That's us. These are the globular clusters. We can see that the globular clusters are not exactly centered around Earth. They're centered around presumably the center of the galaxy. Now, these are galactic coordinates. Galactic coordinates are polar. This gives you the angle, the direction, and then there's some radius of how far away. Globular clusters are indicated by the black dots. The distances from the sun have been rounded to the nearest kiloparsec. 1 kiloparsec is 1,000 parsecs, making multiple clusters to appear to be at the same distance. The dots at the edge of the cluster, at the edge of the graph, represent clusters that are farther away than 19 kiloparsecs. The farthest cluster is 36 kiloparsecs. Estimate the center of the distribution of globular clusters. This is number 5. The best way to do this is to have a small circular object about the size of a quarter or water bottle cap, and try to include as many globular clusters as
Lost my
possible.
quarter.
Sorry that? Try to include as many globular clusters within the circumference of that object. Okay, I can already see where I think it is. Can you guys, do you see where the center of this bad boy is? Can you guys look at this and tell me where you think the center is?
I
Where-
think so. It's like
Yeah,
around like the 7-ish circle towards like the 360.
yeah. So like somewhere like that. Wait, hold on. You guys can't see what I'm doing. Hold on. Do you see how there's kind of like a big chunky clump there? Chunky clump? Do you see that?
Yeah.
I think that. I think that's it. How y'all feeling about that? You like my moves? Okay. Mark an X on the graph at the center of the distribution. So it's about there, right? Actually, if you think about it, it's probably right there. That's why they have galactic longitude at 0 degrees. They define galactic longitude towards the Sagittarius A-star cluster, right? Does that make sense? They want the center of the galaxy to be the center of galactic longitude coordinates. Okay, so estimate the distance from the sun to the center of the distribution. Now, each of these are 1 kiloparsec. So there's the sun.
It's 8.5, right?
That's the, who said that?
Devin.
Devin, that's the actual answer is 8.5 kiloparsecs, but let's just make sure that we got that. 1, 2, 3, 4,
7.5.
7. Oh, maybe this line is, no, that's 2. We didn't count correctly. This circle is 1, right? We are actually at 8.5. We actually got 8.5 kiloparsecs. Now, Devin, did you say that because you were reading it from the graph, or did you say that because you've heard that before?
No, I was reading it from the graph.
You are cool, dude. Can I tell you something? All while I was in graduate school or undergraduate, it was always, yep, center of galaxy, 8.5 kiloparsecs. So as soon as you said it, I knew the answer was correct. Okay, estimate the radius of the galaxy based on the overall full extent of the distribution of the clusters. So I would say that the radius of the galaxy goes from like, sorry, the diameter of the galaxy is from like there to there, right? They told us the most distant one is 36 kiloparsecs.
So the radius would be 18?
8.5, 9.5, 10.5, 11.5, 12.5, 13.5, 14.5, 16.5, 17.5. So you said 18.5?
Yeah, or 18, but 18.5 makes sense.
Well, I don't know if we're going to get it that tightly. 18. Okay. I like it. I like that it's student driven. So do you think we should use 18 or 18.5? I don't know. 18?
Yeah, I think 18.
All right, thank you. Longitude to the center of the distribution is 0 degrees. That's the idea behind galactic longitude. We are masters of the galaxy. We now know the distance to the galaxy, the size of the galaxy, and the direction of the center of the galaxy. So set your course for 0 degrees longitude, 8.5 kiloparsecs away. Congratulations. You've wasted another hour of your lives learning about galactic astronomy. Please turn in everything that you wrote on, okay? Turn in the whole thing, whatever you got. Oh, you know what? There were some extra questions.
No.
Okay, fine. We'll skip them. Fine. We'll call it there. Is everyone cool? All
I'm
right, you
good.
got-
Thanks.
Yep. Now look, one class left. Let's make it a good one, okay? Everyone be there. We're going to do a problem set. What's your question, Austin? A concern, actually. Could you? Okay. Maybe you should speak it through the microphone. So that people-
I'm just a little nervous to say it, Professor. I'm just a little nervous to explain what's going on.
All right. Is this something we have to talk about offline, or?
I mean, you know, I could have some witnesses to my demise. I don't, whatever. I don't know if it's entertaining. It doesn't need
Okay,
to
all
be-
right. Just get to the point then.
All right. So last week, I believe on Tuesday you accept labs, and on Thursday you accept homeworks.
Yeah, but I give you until the end of the week because I'm really generous and nice.
Very so nice, so generous. However, you also have some students that are forgetful, and when they're going through moves and, you know, crazy things like that, they may have forgotten to submit something. You may have said last time they forgot that it was the last time. However,
Well,
they may really.
If you were smart, before you were talking to me about this, you would have gone over to Blackboard. Hold on, wait. You would have gone to Blackboard and recognized that I hadn't closed it out yet, and you would hastily submit them before I decided to grade papers. If you look here, homie, for the period luminosity, it's still available to students. So you still have the ability to submit it. But I am going to close that down maybe tonight.
Okay. Well,
So
clearly not that smart. However, by the time you close it, it'll be in there. So no worries on my end.
then I can't really not grade you or penalize you if you get it in before then, right? Of course, if you don't get it in before then, that
Well,
might
then I'm okay.
tempt me to not give a shit about your problems, right? Because they're so manifold, I can't even begin to pick them up and sweep them into my little dustpan. So
That's
So-
that. Just remind me of my manifold problem.
one of which is, where's my PS5? Okay, now listen. Thanks for the
Number
hot tip
one.
about PS4 and Cyberpunk. I'll pass it on. And Austin, get that stuff in now. Do it now.
Got it.
Hey, if Austin's girlfriend is there, make Austin do his homework, okay?
I tried to, but he doesn't listen.
That is such BS.
I stay here and I listen to your lecture most of the time. more
You've
than
got to
often.
clean up his act, okay?
I will.
Okay, I forget your name, but we're holding you responsible for Austin's homework from now on, okay? You're in charge.
This is great.
Okay. All right. Love you all. One more class to go, and then we're done with Fall 2020 astronomy. So we'll see you on Thursday, okay? Over
Thank
now.
you.
Bye.